So welcome back for those of you who want to come back and have a look at this extension. Now obviously in the main video we said that we're going to use this extension to try to understand under what circumstances we can consider gravitational field strength to be a constant. Now in order to do that we'll first work our way through the example that you can see on the screen, and then we'll sort of draw some information out of that and get an idea of when gravitational field strength at least can be considered to be a constant. So there's a question for you. What is the percentage difference between the gravitational field strength at the top of Mount Everest and at sea level on the Earth? Now, if you don't already know what the height of Mount Everest is, it is 8,849 metres. Now, obviously, as usual, pause the video, go and have a go at it, and then come back when you think you've got an answer. Now, firstly then, we need to remind ourselves how we calculate a percentage difference. So in order to calculate a percentage difference, we would take the difference between the two values. So here it would be the difference between G at sea level and G at the top of Mount Everest divided by G at sea level, and then obviously we would multiply that by 100 to convert it into a percentage. The next stage, of course, is to calculate some gravitational field strengths, and we know that the equation is minus gm over r squared. Now for r, obviously r at sea level, we're just going to take the radius of the Earth, so the radius at sea level will be 6,370 kilometres, as it says on your data sheet. For the radius when we're on the top of Mount Everest, well, all we're going to do is we're going to take the height of Mount Everest, that 8,849 metres, and we're going to add it in to the radius at sea level. Now, a couple of different ways we can do this. If you really want to stick with the exact value, 8,849, you're more than welcome to. But of course, 8,849 metres is just short of 9 kilometres. That value that the datasheet gives you, 6,370 kilometres, really is only to three significant figures anyway, so going all the way down to 8849 is way too many sig figs than we need. Probably the easiest way of doing it is just to round it and call it 9 kilometres, and therefore the height above at least the centre of mass of the Earth would be 6,379 kilometres. Now for this one, we could do an algebraic method, but to be honest, for this one I just decided to do a little bit of a brute force and ignorance method, to be honest, and use the memories on the calculator to my advantage. So G at sea level, my full calculator answer was 9.829878. 576. That was my full calculator answer. And for G at the top of Mount Everest, I had 9.802160,596. Obviously both of those are newtons per kilogram. Now the way that I did it was just to go back and use the memory functions. Obviously we know that the calculator has 9 different memory functions, and I just used the memory functions I in fact called sea level A and Mount Everest B, and then into my calculator using the alpha functions I just did A minus B over A multiplied by 100. And that gave me an answer, once you round, of 0.28%. Now, again, I must admit that I've probably been a little bit lazy here. If I was being really strict with myself, I should have made these two both minuses. But at the same time, when you look at this equation over here, A minus B over A, if all three of those are minuses, all the minuses just cancel each other out anyway. So it doesn't really make a massive difference. Obviously, if we were being strict to ourselves, we would put the minus in, but we're going to get the same answer anyway. Anyway, when we have a look at the answer then, we get a percentage difference between gravitational field strength on the surface of the Earth, at sea level on the Earth, and at the top of Mount Everest as just under 0.3%. Now again, if we go back to having a look at all of the practical work that we do, if you were ever to get a final percentage uncertainty of 0.3% or even less than 0.3%, then I'm sure your practical teacher, quite rightly, would probably accuse you of cheating in some way, shape or form. In other words, you look at the distances that we can get to without propulsion on the Earth, we've only got a percentage difference of 0.28%. Even if we go even further out and say that even further in and say that at only 1 kilometre above the surface of the Earth, the percentage difference then becomes 0.031%. And again, at that point, especially as soon as you get underneath 0.1%, at that point you've got to three significant figures, the values are going to be basically the same anyway. Within sort of unlucky rounding, they're going to be the same anyway. So really, let's answer the question we originally set out to answer. At what point can you consider that gravitational field strength is a constant? Well, personally, I would say that in context of the Earth, if you're only dealing with a difference of less than 1 kilometre as far as delta H goes, then we're more than happy to do that. Normally, the way that we would write that is we would say that obviously we know the equation EP equals mg delta H, and we would normally just say that applies when delta H is, and if we use the double inequality, that means orders of magnitude smaller than r, which is the radius of the Earth. So really then, it's a lot of the time it is a bit of a judgment call to understand when we can deem something that we know does vary, when we can treat that as a constant. Normally the easiest way of doing it is just to take a couple of examples, do a quick calculation, work out any percentage differences, and especially if you get really low percentage differences like 0.03% or even lower than that, at that point I think we're normally quite happy that at least in most circumstances we can assume something, as in gravitational field strength in this example, to be a constant. So that equation, as we said, you were taught at GCSE, EP equals mg delta H. Again, that applies. It's not necessarily a wrong equation. It can be used, it can be applied under certain circumstances when we have a very small delta H compared to the radius of the Earth. Thanks again for coming in for the video. I hope you found that useful, and we'll see you in the next video.